Hello, everyone. Today we'll discuss a topic dedicated to uniformly accelerated motion, but today's lesson is divided into two parts. So, first part is a lecture, as you can see, and the second part is dedicated to the laboratory work with the help of VFox app on our phone. So, let's move on to our presentation. Before knowing about uniformly accelerated motion, we should know about types of dimensions and types of motion in physics. So let's go. First of all, let's discuss about dimension. We have three types of dimensions in physics. First type is one-dimensional system, second type is two-dimensional system, and third type is a three-dimensional system. So one-dimensional system is when you can only go forwards or backwards. For example, you can describe the movement of the ball. If you drop a ball, there we can see it moves like up and down. It only has one line of movement, right? It's not moving side to side. It's not moving along the projectile motion. It only moves along one line. And it means that it moving in one-dimensional system. Two-dimensional system, we can take an example of a map. There, you have such destinations as north, south, or east, west, for example, right? You can just imagine a triangle on a map, and the imaginative hypotenuse of this triangle is basically a two-dimensional movement. So, let's go back to our example. If it moves in two ways, two lines, right, side to side, for example, it's two-dimensional system. For example, about ball, right? If we are throwing a ball side to side, it moves in two-dimensional system. Then three-dimensional system, it's a real life movement. So if the ball flies through the air, it's moving in three dimensions, right? Right. How do you imagine this process? For example, we take three people. First is standing there, second there, and third there. So first person is throwing a ball for second one, and second one is throwing a ball for third one. So basically, the initial position is position A of a first person, right? And the final position is the position of third person. Let's say position C. So the movement of a ball started with position A and ended in position C. So that's one line, right? But it had actions from 1 to 2 and 2 from 3, from 2 to 3. So it moves side to side, right? And also, if you're throwing a ball, it not only moves along a straight line, right? It moves like a projectile motion, uh, along a projectile motion. So it has its own curve of motion. So it's also moving in z-axis if we're imagining the axes from algebra. X-axis, like x-axis, let's take it like that. Y-axis, it's moving up because you're throwing a ball, right? And z-axis, it's when it moves side to side, and also from projectile motion, we can take it as z-axis too. So okay, we now know about dimensions, and let's talk about types of motion in physics. So actually we have 6 types of motion in physics, but we are not taking Brownian motion yet because it's the topic from 11th grade. And let's talk about each type one by one. So translational motion, as we can see, there's an example of track. Translational motion refers to movement where every point of an object moves the same distance in the same direction. So if we'll take some car or track, as I said, right, it moves only in one direction. It only has one line of movement. So, and also it has no rotation in movement, right? Then we have rotational movement. As I said, there are no rotation, but there we have a rotation because it's a rotational movement, logically, right? So, a rotational movement is when an object spins around an internal axis. For example, there we have like internal axis, that's the middle of the object, and the object itself spins around this axis. По своей оси крутится, да? Оси. Okay, then circular motion. There, an object moves along a circular path. As an example shows, this little ball moves along a circular path. That's why we call it circular motion. And please, the difference between rotational and circular motion is that rotational motion is when an object has its own internal axis and spins circles around its axis, right? And circular motion is when an object spins around circular motion, not its own axis. Then we have oscillatory motion. Actually, oscillatory motion can include sine and cosine functions from algebra that we all know. And there in oscillatory motion, sorry, oh my God, repetitive back and forth motions around a central point take place. So such graphs has their own period and length of the wave, right? Also, we can include sound waves as an example of oscillatory motion. Then random motion, it's a chaotic motion of an object. In atomic physics, we have molecules and atoms that are moving chaotically in the air, for example, right? Or other objects. Then we have these two men. Who are they? How do you think? I'll give you 5 seconds to write in comments below. Okay, so this one we all know him. His Isaac Newton, who created three basic laws in mechanics, sorry. And there in the left corner, in the left side, we have Galileo Galilei. He first developed the concept of uniformly accelerated motion that we're discussing now. And he developed this idea in late 16th century. Just imagine 16th century. And he was the first man who did such laboratory works that are dedicated to uniform accelerated motion, logical, with inclined planes. Even though he did some works with inclined planes, we still can calculate it in straight line, like in other surfaces, not only inclined ones. And Isaac Newton later formalized it with his laws of motion in the 17th century. So we all know his second law, F equals to ma, right? So that's the historical origins of our topic. So, as I said, the concept of uniform accelerated motion was first developed by Galileo Galilei, and Newton's laws unified Galileo's observations into a broader framework of classical mechanics. Let's move on to the formulas. Okay, so, there we go. So, we all know two basic formulas of mechanics. First formula is A equals to change in velocity divided by change in time. Okay, and also we have vectors. Vectors are the special signs that are put to the top of those quantities that have a known direction. If the quantity has direction, then it has a vector at the top of it, right? Do we see it? Okay, there. So that's the acceleration there and velocity, change in velocity divided by change in time. Okay, second formula is about distance. Distance equals velocity multiplied by time. But there we have not the basic velocity, but the average one. The average velocity we take in uniformly accelerated motion because in the motion of an object we have an initial velocity and a final velocity. Why? Because the final velocity is always different from the initial velocity because we are accelerating our motion uh, after the known time, right? Um, the motion is accelerated, so we have different velocities in different points of motion. So, how do we find the average velocity? Basically, it's an arithmetical medium of the velocities at all. So we have final velocity plus initial velocity divided by 2. Arithmetical medium, we all know that from classical algebra, classical math. And if we'll continue our formula with this one, let's replace the average velocity with its own formula. It will look like this, right? But from the first formula, we can say that time equals to velocity divided by acceleration, right? This one. But there, as I said, we have two types of velocities, so we should include them to this formula too. So it means final velocity minus initial velocity divided to time minus 0. Why 0? Because we have only one time during the whole movement, during the whole motion. So that's the formula of acceleration. And if we will take the time from that formula and write it down to this one, it will look like this. So you see it? V plus V0 divided by 2 multiplied by V minus V0 divided by A, acceleration. So that's our perfect formula, and now we will then solve it in a mathematical way. So it means that V squared minus initial velocity squared divided by 2A. And that's the formula for distance without time. Without time. And now let's solve it with time. We have this formula right there, right? But there we have a final velocity. But if we don't have a final velocity, what should we do? Okay, so the formula of final velocity, guys, is, there we go, initial velocity plus acceleration multiplied by t. Where did we take this formula from? Of course, from first formula. There we go. V, velocity, equals to acceleration multiplied by time plus initial velocity. So we take it from there. X. That's the rate. And let's just replace this V in this formula with the one that we wrote 2 seconds before. So there we go. Oh my God, sorry. It means that V0 plus AT plus V0 divided by 2 multiplied by T. There we go. And what can we do in this friction? In this equation, we can, of course, add two initial velocities. It will be 2V0. And then 2V0 divided by 2 plus A T, right? T divided by 2 squared. So there we have AT. Let's open Okay, let's open the brackets and multiply all of these to t. We will add two initial velocities. That will be 2v0 multiplied by t, right? Multiplied by t divided by 2. Then we'll just cut these 2's and plus at. We already have t there. Multiplied by t, it would be at squared, right? At squared divided by 2. So this equation, then let's cut out 2. It would be v0 multiplied by t plus at squared divided by 2. And all of that equals to what? Of course, distance. That's the formula with time. Learn these four formulas. First one is this formula with time. Second formula is with time, but with the final velocity known. Second formula, right? Third formula is the formula of distance without time, this one. And fourth formula is the formula of average velocity. These two formulas are known for you, right? You can also write down to your copybooks this one with initial and final velocity. So formulas are done. Let's go back to our presentation. So impact of physics uniformly accelerated motion is a new core concept in physics education, especially in mechanics. It applies to free fall projectile motion, as we said before, and vertical acceleration, among others. The equations derived from Galileo and Newton's works are still used today in labs, and we will use it together in our laboratory work in the second part, also in engineering and simulations. Thank you for your attention. Let's move on to the second part, to the laboratory work.